Hang on.
No. Gaurav will just start the live sharing. Then I will introduce you, and then I'll hand over.
Okay, sir.
Hang on.
No.
Okay. Yeah, Krishnan, go ahead. Okay, I think he dropped off. So let me begin. It's a pleasure to introduce Nargish Punia, who will be speaking on partition classes arising from parity, differences, and repeated small parts. And this is joint work with Rahul Kumar, who has been a speaker in our session. Go ahead, Nargish.
Thank you, sir, for the introduction, and also thanks for the opportunity to speak in this seminar. Hi, everyone. My topic of today talk is on partition classes arising from parity, differences, and repeated smallest part. So in this talk, we will define some partition functions and will give relation between them, and we will see how this relation will forward us to find an analog of Euler extension theorem. And we will find some elegant properties of partition functions with repeated non-negative smallest part and give some elegant refinement in Euler extension theorem. And we will end with some future questions. So before starting, I would like to recall the definition of a partition. So a partition of a positive integer n is a finite non-increasing sequence of positive integers such that their sum is equals to n. Here these lambda i's are called parts of the partition. Now, we are starting with one of the most celebrated theorem in theory of partition, which is Euler theorem. And it states that for any non-negative integer n, we have an is equals to bn, where an denotes the number of partition of n into distinct parts, and bn denotes the number of partition of n into odd parts. Now, very recently, Andrews, Kumar, and Yee give an extension of this theorem by adding two partition functions, namely Cn and Dn. Basically, they state that for n greater than 0, we have An is equals to Bn equals to Cn plus 1 equals to half of Dn plus 1. Here, this Cn counts the number of partition of n with largest part even, and parts not exceeding half of the largest part are distinct. And this partition function Dn is the number of partitions of n into non-negative parts where the smallest part appear exactly 2 times and other parts are repeated. Now from here we can clearly say that for n greater than equals to 2, d of n is always even, as d of n plus 1 is equals to twice of an. Now the question is, if for n greater than equals to 2, d of n is even, so is it possible to break it into two disjoint classes of same cardinality? So the answer is yes, we will see it very soon. But before going on that, I would like to recall theorem by Glacier, which is an extension of Euler theorem. So basically it states that for any non-negative integer n, we have amn is equals to bmn, where this amn be the number of partitions of n into parts repeating less than m times, and bmn be the number of partitions of n into parts not divisible by m. So clearly if I take m is equals to 2 in this case, so we will get Euler theorem. Now, very recently, Lin and Zhang also give an extension of this theorem by adding this partition function ekn, and they state that for n greater than equals to 0, we have bkn is equals to ekn, where ekn denotes the number of partitions of n with the largest part m is not a multiple of k, and the parts which are not exceeding this quantity appear at most k minus 1 time. Also, they state that we have bm dash n is equals to cm n plus 1, where bm dash n be the number, sorry, where bm dash n be the number of m regular partitions of n with largest part j is congruent to minus 1 mod m. Also in this direction, Andrews and Dhar also give a beautiful identity between the generalized version of the partition function Cn and Dn, and this identity is true for almost all n. So we have this Dmn to be the number of partition of n into non-negative parts where the smallest part occurs exactly m times and all other parts repeat less than m times. Now, before motivation to proceed further, I would like to again the definition of Dn, which is the number of partition of n into non-negative parts where the smallest part appear exactly 2 times and no other parts are repeated. Here we should note one thing, that here we are allowing non-negative parts, means we are considering 0 as a part also. Now the question is, what is special about this 2? Why we are not taking 3, 4 and so on? So what is special about 2? What happen if the smallest part is allowed to appear an arbitrary number of times, let's say k times, and while all other parts remain distinct? So let us denote this type of partitions by dkn. And now another question is, if I take this type of generalization for dn, so what will be the analog of the theorem which is given by Andrews, Kumar and Yee? So here our main motive is not just to find a generalization of the theorem which is given by Andrews, Kumar and Yee, but our motivation is also that is this analog help us to comment on the parity of dkn. As we know, dn is always even for n greater than equals to 2. So what about when k is 3, 4? So in that case, what will be the parity? Is this analog help us to comment on this thing? So we also interested in this thing. Next, we also give an analog of either pentagonal number theorem, but we note that very recently Andrews and Bechroy studies the function SPT-KDN, which counts the number of partition of n in which the smallest part occur exactly k times and remaining parts do not repeat. Here this partition function SPT-KDN differs from our partition function DKN only in sense that here we are allowing non-negative parts as well. Now, before stating our results, we define some partition functions. Let bken, respectively bkon, denotes the number of partition of n in which all parts are odd, except possibly for at most k minus 1 distinct even parts lying in this interval, where 12 minus 1 is the largest odd part and the number of such distinct even part being even respectively odd. So basically what we are doing, so we are counting those partition where all parts are odd and the distinct even parts can be at most k minus 1 and they belongs to this interval, where this interval depends on the largest odd part present in that partition. For example, let's say if I take k is equals to 1 in this case. So when I take k is equals to 1, then this interval makes no sense. It means I am taking 0 number of even parts. So in that, for k is equals to 1, all the partition belongs to this category bken, and in that case bkon is equals to 0. In the same sense, also we can note that for k is equals to 1, bken is nothing but bn. Bn means where all number of all partitions where all parts are odd. So in the same sense, we can define partition function cken and respectively ckon, which denotes the number of partition of n in which the partitions contain an even part, let's say 2l, and the all parts which are not exceeding l are distinct, and the only parts which are larger than 2l can be at most k minus 1 distinct even and lying in this interval, and the number of such distinct even parts being even respectively odd. For understanding more of this definition, we can take an example. Let's say I'm taking n is equals to 8 and k is equals to 2. So for k is equals to 2, our intervals contain only one element, which is of the form 12 plus 2. So let's say if I want to find those partitions which are counted by B2E8. So for that, we have to take even number of parts from this interval. Now this interval contain only one element, so we are left with only one choice, that we are taking no elements. So in this category, we have those partitions in which all parts are odd. Now, in same sense, if we find for B2O8, so for that, we have to take odd number of parts from this interval. It means now there is only one, so we are taking an even part of from 12 plus 2. So under this category, we have those partition in which all parts are odd and an even part of the form 12 plus 2, where this L depend on the largest odd part present in the partition. So in same way, we can find all the partitions counted by C2E9 and C2O9. But here we observe one thing, that the even categories of B2 and C2 are equal, and the odd categories of B2 and C2 are also equal. But this is not just a coincidence, but our next theorem support this fact, and it says that the even categories of BK and CK and odd also odd categories are related by this relation. Here, if I take the difference of these two equations, then that is also of equal importance. We will see it. Now, in our paper, we will give a combinatorial proof of these expressions, but at this time, for simplicity, I'm just taking k is equals to 2. So when I take k is equals to 2, observe that B2En is equals to Bn, as I already mentioned. We are left with only odd parts, so this is equals to Bn, and C2En plus 1 is equals to Cn plus 1. Now, since by theorem of Andrews-Kumar and Yee, we know B of n is equals to C of n plus 1, and their bijection provide a bijections between the set of partitions counted by B2E and C2E by using the bijection between B and C. Now, for the odd categories, we need a bijection. So for that, we consider a partition which is counted by C2ON. Then it is of the following form. We have one even part from the interval 12 plus 2 and another according to the definition. Now, if I consider this portion of the partition starting from 2L, then this is nothing but a partition counted by C2E and minus 12 minus 2. Now, from this fact, this partition can be converted into a partition which is counted by B2E, and let's say this partition is mu. And finally, this partition appending with the part 12 plus 2 yields a partition which is counted by B2O and minus 1. In the same sense for reverse order, we are considering a partition which is counted by B2ON. So according to the definition, this partition look like this. Where we have only one even part 2m and other parts are odd. Now, again, if I consider this remaining portion of the partition, then this is nothing but a partition which is counted by B2E and minus 2m. Again, from the previous concept, we can convert it into a partition which is counted by C2E and again joining with the part 2m. This is the partition counted by C2O and plus 1 as required. Now we can see that for k is equal to 2, we have a simple bijection. But like for k is equals to 3 and so on, we have to be more careful. Why? Because for the case k is equals to 3, here we so this type of relation doesn't exist because B3En is not equals to Bn. So we can't use directly the fact that B of n is equals to C of n and to be proceed. So we have to be more extra careful. And one thing, for k and higher values of k, the interval should become large. So the picking of the parts from the interval should increase. So we have to be more careful about k is equals to 3 and so on. Now, as I mentioned, if I take the difference of this partition function, that is also of equal importance because it's directly connected with the partition function d2k in this given by this expression. Now, from here, it is immediately implies that Bn is greater than Bkon, and the even categories of Ck is greater than odd categories of Ck. Basically, that is a fact that doesn't seem to be easy to establish directly. Also, from here, we can see that for n, when n is greater than this number, this d of 2k is always even, as same d of 2k n plus 1 is equals to twice of this. So again we have a question that if d of 2k n is even, so is it possible to break into two disjoint classes and so on? Now we can prove this theorem by considering the generating function for d2k, means the smallest part repeat exactly 2k times and other parts are distinct with some extra factor. Now this can be written as this by multiplying and divide by minus qqm, and this second factor can be written in terms of this sum by using Euler's identity with t is equals to q raised to the power 2k, and after that, this first part of this expression, after multiplying and divide by q infinity, we will get q square infinity. In the same sense, if we multiply minus q infinity and also divide, so from here we also get q square infinity. So taking common out all the common factors, we will get this expression. Now we can apply on this term Euler's identity with t is equals to q raised to the power m plus 1, and in this factor we apply Euler's identity with t is equals to minus q raised to the power m plus 1, and we will get these two sums. Now again we take the factors common and we will reach to this expression. So from here it is very clear that if I taking n is equals to odd, then this expression is equals to 0. So I am taking n is equals to 2n. So when I replace n is equals to 2n in this case, so it is equals to q square infinity double sum this expression. Now separating thus both sums for m and n and applying again Euler's identity on the summation for m. So we will get this expression. And this is nothing but the generating function for the difference of the partition functions counted by CKE and CKON. And now finally, on comparing the coefficient of q raised to the power n both sides, we will get our theorem. So here, our next result connects dkn with another type of partition. This P1 pk minus 1 dash, P2 pk minus 1 double dash. So here this theorem says that if I take k and n be any natural numbers, then we have akn is equals to half of dkn plus 1, where this akn is given by this expression, and where this p1dn counts partitions of n into distinct parts whose smallest part exceeds 1, and p2n denotes the number of partition of n into distinct parts for which the difference between the two smallest part is at least 2. Moreover, the function pk minus 1 dash dn enumerates partition of n in which all parts are distinct, except that the smallest part must be 1 with multiplicity k minus 1. In the same sense, we can define pk minus 1 double dash. So together all the results, we now finally ready to give an analog of Euler extension theorem, which is given by this expression, which is true for when n is greater than this number. Now from here, if we observe that, as I already mentioned, when n is greater than this number, so d of 2kn is even. Now the question is, from this expression, we can only comment on the parity of d of 2k. So what happens when this number 2k is replaced by an odd number? So in that case, what will be the parity of d of n? And another question is, from this expression, we have n is greater than this number. So what about the lower values of n when n is less than equals to this number? So in that case, what will be the parity of d of n? So all this discussion, so it is very reasonable to ask these three questions: that is dkn is always even for any k? So if it is even, so is dkn always classified into two disjoint classes? And can we find an exact lower bound for n for which we can always say that it is always even? So we will answer to all of these questions, but before going on that, I would like to recall Euler pentagonal number theorem, which says that the difference of these two partition functions is equals to minus 1 raised to the power m if n is a pentagonal number and 0 otherwise, where this PEDN, respectively PODN, denotes the number of partition of n into an even and respectively odd number of distinct parts. Now I define class. So class basically contain those partition which are counted by dkn, means those partition in which smallest part repeat exactly k times and other parts are distinct. Now I define two subclasses, subclass 1 and subclass 2. So basically subclass 1 contain those partitions of class in which the other parts other than the smallest are even in counting, and subclass 2 contain those partition of this class in which the parts other than the smallest part are odd in counting. So if I denote the cardinalities of these subclasses by dken and dkon, so clearly these two subclasses are disjoint, and if I take the union of both of these, then this is equals, this represent the whole class. And so from this concept, we can clearly say that dkn is equals to dken plus dkon. Now our goal is to prove dkn is always even. So, or for what values of k it is even or not. So for that, it is enough to show that the cardinalities of these two are equal. So in any way, if we are able to prove on the cardinalities of these that they are equal, then we can directly comment that d of kn is always even. So our next theorem says that the difference of these two cardinalities is equals to minus 1 raised to the power m if n is up 1 and k minus 1. And if it lies between k minus 1 and half of k into k minus 1, then this is given by the difference of these two partition function. And otherwise, it is 0. Here, these two types of new partition function denotes the number of partition of n into an even number of distinct part or respectively odd, but with an extra condition that no parts exceeds k minus 1. Now we can prove it by taking the generating function for the difference of cardinalities. So here the generating function for this is clearly given by this summation. Now we can multiply and divide by QQN to this expression, and we will get QQ infinity summation n 0 to infinity QNK by QQN. Now we apply Q binomial theorem on this sum to get QQK minus 1. Now clearly this is nothing but the generating function for the number of partition into distinct parts where the parts are of size at most k minus 1. So basically it is the generating function for this difference. Now we can observe that here if I expand this term, this expression, then from here the highest power of q can be 1 by 2 k into k minus 1. So if I comparing the coefficient of q raised to the power n both sides, so for n greater than half of k into k minus 1, the coefficient is 0. So the third part of our theorem is proved by this explanation. Now we only observe for n when n is less than equals to half of k into k minus 1. So when n is less than equals to k minus 1, so clearly this difference is nothing but PEDN minus PODN. As we know that when a number is less than equals to k minus 1, then no part can be exceed from k minus 1. So this difference is equals to PEDN minus PODN. Now we can apply Euler's pentagonal number theorem on this difference, and from there we prove over the first part. Now if I take n lies between k minus 1 and less than equals to half of k into k minus 1, then on comparing the coefficient of q raised to the power n both sides, we arrive at the second part. Now in theorem, we can clearly observe that when n is greater than half of k into k minus 1, this is equals to 0. Means we can say that when n is greater than half of k into k minus 1, d of kn is always even. So this is our next corollary, which says that when you are taking n is greater than k into k minus 1, cardinalities of these two subclasses are equal. And from here, we can comment on the parity of d of kn. Now, we can observe that in our theorem of analog of Andrews, Kumar and Yee, for where n is greater than 2k minus 1 into k 2k minus 1. So this is the bound in that theorem. But here we have a bound n is greater than k into k minus 1. So basically we refined it. Now we can understand these subclasses and cardinalities concept by taking this example for n is equals to 7 and k is equals to 2. So if I'm considering D27, so these are all the partitions which are counted by D27, means smallest part repeat 2 times and other part are distinct. Now among these four partitions have even number of parts greater than the smallest part, and these four partitions having an odd number of parts greater than the smallest part. So clearly these four partition belongs to subclass 1, and these four partition belongs to subclass 2. And the here the cardinality is 4, here also cardinality is 4. And the union, these two are disjoint, and the union of these is equal to the whole class. Now this concept of that we show that the cardinality of two subclasses are equal, so it give a more refinement in Euler extension by Andrews, Kumar and Ye. So basically we can write this Euler extension theorem in a more refined way by adding these two partition function d2e n plus 1 and d2o n plus 1. Now we have a more refined version. Basically we can ignore this term 1 by 2, as d of n plus 1 can be written as twice of d2e n plus 1. Also, we can do the same for the generalized version of the analog. Now, our next theorem represents the generating function for dkn in terms of q symbols. We can prove this by proving its finite analog. Here in this, clearly, if I take taking n tends to infinity, so clearly when I take j is equals to 0, then this term and applying n tends to infinity, then this term is 1 by minus q to infinity. And when j is greater than 0 and applying n tends to infinity, then this goes to 0. So by applying n tends to infinity, we will come to our expression 4. Now the beauty of this expression is not just the fact that we are writing the generating function for dkn in terms of q symbols, but it is a very interesting property that it gives a recurrence relation for dkn and many more identities. So which is given by as an example, we can see from a corollary, if I take k is equals to 3, then we will get this type of identity which connecting d3n with the partition function an. And also, if we solve our expression 4, then we will find that we have a recurrence relation of this type between for d of k, which says that d of k and d of k minus 1 is equals to this expression including the partition function an. Now we can prove it analytically by using the previous expression, but we can also prove it combinatorially. So for combinatorial purpose, we take a partition which is counted by this category, means either it is counted by dkn and either counted by dk minus 1, and we will map this partition into a partition which is counted by these categories. So we will find a 1 1 onto bijection or 1 1 onto function. So for that, we take a partition which is counted by left hand side. So either it is counted by dkn or either it is counted by dk minus 1. So so for case first, if we take lambda is counted by dkn, so clearly it is of the form this, where the smallest part repeat exactly k times and other parts are distinct. So now there are three cases. If either smallest part is equals to 1, it is greater than 1. So if lambda L is equals to 1, means smallest part is equals to 1, then what we will do, we subtract 1 from each of the first k minus 1 smallest part to obtain a partition which is counted by dk minus 1 and minus k plus 1. Of course, if lambda L is equals to 1 and we subtract 1 from first k minus 1 parts, then we will get a partition which is repeating k minus 1 times and smallest part becomes 0 and all other parts are distinct. And obviously the second smallest part is equals to 1, as we are subtracting 1 from the first k minus 1 smallest parts. And the second case is if smallest part is greater than 1, then again we are subtracting 1 from the first k minus 1 smallest parts, so which again yields a partition which is counted by dk minus 1 and minus k plus 1. So in which two smallest part are consecutive and the smallest part is at least 1. And the third case is when lambda L is equals to 0. As in our definition, we are allowing 0 parts as well. So lambda L can be 0 as well. So if lambda L is equals to 0, then clearly it is a partition counted by an. So clearly if this is equals to 0, so we can neglect them and we can clearly say that this is this is nothing but a partition which is counted by an, means all parts are distinct. So this is case first. Now the case second, when counted by dk minus 1. So we apply the same process. So there can be three choices: either smallest part is equals to 1, either it is greater than 1, or either it is equals to 0. So again, if it is equals to 1, so we subtract 1 from from the first k minus 1 smallest part to obtain a partition counted by dk minus 1, where the smallest part is 0 and other parts are distinct, and with the second smallest part greater than 1. Again, we can do same for lambda L greater than 1 and lambda L is equals to 0. Again, with same concept, is a partition counted by a n. So when we take union of all 6 conditions, then we will find all the partition which are counted by right hand side. So basically, we find a 1 1 onto function between these two types, between LHS and RHS. So this completes the proof of our theorem. Now we propose the following questions for further investigation. So it would be very interesting if we are able to find a direct bijection between these differences and how dk or either with a to k, or as I show that these two subclasses have same cardinality. So it would be very interesting to find a bijection between these two subclasses with those counted by an, bn, or cn, or either between these two. And also we have an analog of the type Euler's identity, and there we show that the difference of these two cardinalities again equal to the sum of difference of other two partition function when n is lies between these number. So again we can find a bijection between these two sides or no. So this is all about. Thank you.
Thank you, Nargish. Any questions for Nargish? So I have a question. Do you have similar kind of theorems for Rogers-Ramanujan type of partitions?
No, sir, actually.
I mean, anybody studying refinements of those?
For Rogers Ramanujan's type partitions.
Yeah,
Actually,
I mean,
I
the
didn't
difference conditions are little different, right? I mean, they also like they also generalize odd equal to distinct.
Yes, sir. Yes, sir. Yes.
So,
I don't think, like, but I think I can try.
All right. And so all your theorems, you are looking for combinatorial proofs or just a few?
No, sir. Like I give some combinatorial proof, but the more questions lie on combinatorial proofs.
Okay.
Because the problem is that the theorem is true for large values of n. As we can say the bound in the theorem in analog of Andrews, Kumar and Yee. So the bound for k is equals to 3. The bound is start from 12 or 13. So there are lots of partitions. So I am not able to even to take an example of the bijection. So how should I start? So I'm facing the problem to find a bijection between the difference with dk and ak.
I see. Okay. Thank you. Nice talk. You finished very fast. So any other questions and comments? Okay, then we will thank the